Hi everybody, so in this video we are going to talk about the difference between convergent and asymptotic series. This is quite important as a discussion to understand the difference between what we usually do in standard calculus, where we typically deal with convergence conditions and convergence analysis of some series, while in perturbation methods usually we derive asymptotic series, and of course it's very important to notice or to know the difference between these two and understand that one is probably in engineering applications at least a little bit more useful than the other. All right, but I don't want to take any position and say that convergent series are bad or good, and neither for asymptotic series. It's just good to understand that each of them has its own strength and weaknesses. All right, so maybe just to fix ideas, let's come back to the definition of a convergent series. All right, so we would say that a series which can be written like this: sum for n's running from 0 to infinity of f and z is convergent, all right, or converges, in the sense of what we usually learn in standard calculus, for a fixed value of z, if for an arbitrary given or chosen, epsilon, which is positive, usually small. This is where the challenge is. It is possible to find a sufficiently large, usually, right? A sufficiently large n, which depends on where we are in the complex plane, if this is a complex number z, and which depends on the small number epsilon that was arbitrarily chosen, such that we can make the difference between the remainder, so the sum from m to n of fn f of z smaller than epsilon for any m and n that you would choose, which are chosen larger than this n0. All right, and of course n should also be larger than m for this to hold. All right, so it means basically that if you're looking at the sequence f0, f1, f2, f3, f4, and so on, so you would expect all those terms to become smaller and smaller as you add them to the previous terms, such that when you cumulate all those terms, you would expect that the sum of these terms in the sequence would converge towards something. And this is translated by the fact that you can play the game, ask someone to give you a small number, epsilon, and you would say that this series converges, provided it is possible to find a value of n0, so it means a place in this sequence, such that no matter where you start adding in the f5, f6, f7, no matter where you start adding and subtracting terms in what follows, no matter where you are, you see that the sum of those terms can be made as small as we want, can be made smaller than this value of epsilon. And of course, if I give you another value of epsilon, which is smaller than the value that I gave, for instance, in the previous run, in the first run, then certainly n0 should grow and should be moved to the right. So we should have a look at the terms which come a little bit further in the sequence. All right, so that's something you should remember certainly from calculus. And then we can also say that a series converges to a certain function, right? That's another concept that is very important, because this is what we want to do here in the problems we tackle here. And so in the very same manner, we say that a series converges So this series converges to a certain function, let's call it fz, for a certain or fixed value of z, for a fixed value of z, if, again, for any arbitrary or for an arbitrary value, small value of epsilon, it is possible to find sufficiently large value of n0, which might depend again on z and epsilon, such that we can make the difference between the sum from n is equal 0 to n of those fn and the actual function or the value of the function that you want to represent. You can make it as small as you want. Provided you truncate at an index capital N, which is larger than n0, okay? So meaning in this case, following the same spirit, right? It just means that you can make the difference or the discrepancy between the result of that summation here and the target function that you're looking for, fz, the one for which you'd like to get a series representation. You can make the difference between these two as small as desired, provided you truncate the series here at a sufficiently large value of n. All right, maybe just an example here. And of course, yeah, what is called, probably it's important to recall this as well, what we mean the radius of convergence of a series, right? So the radius of convergence of a series, of course, it should be convergent, or we hope it is, convergent series is the set of all z values such that the series representation converges to f of z. All right. I have no very good example to share with you, but for instance, just remember from on the real axis, for instance, just remember that if you want to consider, for instance, a representation of 1 over 1 plus x, okay, that would be our function of x. We know that this can be represented by a series whose terms are 1, or let's make it even simpler, 1 minus x over here can be represented by a series whose different terms would be 1 plus x squared, x to the third, etc., etc. And you see that this sequence or this series converges provided x is smaller, strictly smaller than 1. All right. Otherwise, the series is said to be divergent. All right. So in the complex plane, we can expand this and say that the radius of convergence of that sequence or of that series is the unit complex circle, right? That's real axis and imaginary axis. Okay, the radius of convergence would be this area. All right, and so just another example, which might be quite interesting. So we would like to expand this time not a function that looks like this, but we would like to expand a function that is the error function of x. All right, the error function of x is defined as 2 over the square root of pi integral from 0 to x of exponential minus t squared dt. All right, that's the definition. If you want to have a look at what this function looks like, this is what we have, all right? This is the error function for x running from -5 to +5, all right? So you see this is typically a function that rises not too fast, and then it reaches a certain plateau here. There's a horizontal asymptote where actually the error function grows all the way to 1. And it stabilizes over there. All right, so we would expect that, for instance, the error function expressed or evaluated at z is equal to 2 or z is equal to 4 is something that is really close to 1. All right, and so in order to evaluate this integral, in fact, we could just observe that the exponential of minus t squared actually has is an analytic function in the entire complex plane, or so of course also on the real axis, so is analytic. So of course also on the real axis. And actually can be expanded with a Taylor series expansion. All right, so if we use Taylor series expansion of this exponential, we notice that the expression will be the series expansion of the exponential function, right? Where I just replace here the standard argument of the exponential by minus t squared. All right, and actually this function here is convergent. And moreover, the radius of convergence is the entire complex plane. So as a consequence, on the real axis, it means this is the entire real axis R. And great, the way to figure out why this is the case is just because you see that the denominator here with the factorial functional over there grows much faster than what we have at the numerator. And so it means that the different terms that we're going to obtain in this series are getting smaller and smaller. All right, and so if we use this definition for the exponential of minus t squared, and if we push it in the definition of the error function, then we can integrate term by term, and then we end up with the fact that the error function is 2 over square root of pi. We swap summation and integral operators, which is something we can do, because what we obtain at the end is also a convergent series on the entire complex plane, minus 1 to the power n, x to the power 2n plus 1, divided by 2n plus 1, multiplied by factorial of n. All right, also convergent for any x in R. Okay, great. So we can expand this probably and just write down the first few terms. We will just realize that this is something that decreases quite fast. We have x to the third over 3, x to the fifth over 10, minus x to the 7 divided by 42, x to the 9 over 216, then minus x to the 11 over and etc., etc. The full sequence is some terms of the sequence. You see, I've used Mathematica to produce those results. I just use here, I just define here the approximation function, approx of z, which is defined using the formula that we just obtained. And if I want to truncate n here, you see this is the truncation order. If I want to truncate until the 6th term, so after 0, I want to keep 5 terms. So this is 0, 1, 2, 3, 4, 5. This is what we get. I can use this function, of course, to go a little bit higher and explore what's going on if we include more terms in the series. Okay, so we want to make it efficient somehow, let's say, and we want to develop a computer program in order to compute the error function of x. And if we want to use a computer program to compute this, then at some point we'll have to truncate the series and drop the remaining terms. All right, this is typically how computer programs work. And so we can evaluate whether this convergent series is doing a good job or not in order to get the approximation of the error function. All right, and so to do so, what I just provided here is the value of the error function of t when t is equal to 1 for different truncation orders. All right, so you might not be familiar with the nomenclature in Mathematica. This just means that I'm creating a table here with 4 different columns. All right, 1, 2, 3, 4 columns. The first one is n, the truncation order. The second one is the error function of t, which is, as we grow the truncation order, you see n is running from 1 to 15. The error function here is constant because it does not depend on n. So I just copy pasted this value in all lines just to make sure we have something to compare with. In the third column, we have the approximation that is generated after having truncated at a certain order. And that's the discrepancy or the error. And so you see that using one term, the estimation is 0.75, then 0.86, 0.838, and then 843, and so on and so on. And you see that as we go through iterations, we finally converge. This is the definition of a convergent series, right? And we see that we don't need to keep too many terms in order to get an accurate result. So I would say if you want to keep a result which is accurate with an accuracy which is about 10 to the minus 6, you see that we can keep only 7 terms in that sequence or in that series, and we can truncate after 7 terms, all right? So a computer program would do a good job here by truncating over there, all right? And so somehow you can just figure out that this value here, which is the error, is something that you can compare with the small epsilon that we had before, and 7 here is the large value of n that you need to select in order to make sure that if you truncate at that order, you don't make a too big discrepancy, too big error. All right. Let's see what this provides when n is equal to 2. So we have exactly the same thing, except that this time t or z, the value at which we want to evaluate the error function, is equal to 2. All right. So this is n, the truncation order. This is the error function of t. That's what we said. You see, we do expect the actual result to be close to 1. This is our truncated approximation, and this is here the error. And so you see that we have 100% error, and then 187, and then it grows down, and we need to keep more than 15 terms. I stopped here in the table to generate after 15 terms, but we need more than 15 terms to make sure the discrepancy is smaller than 10 to the minus 1, 2, 3, 4, 5. More than 15 terms in this case for error to be smaller than 10 to the minus 5. All right, it's not a big deal, right? Because computers can solve problems like this. If you need more than 15 terms, this is all right. This is, of course, it's gonna take some time as computational resources, but this is probably still fine. And so if you want to keep going a little bit further again, you see that when t is equal to 3, the value of the error function comes closer to 1, but we don't necessarily come with crazy numbers, right? Because this is only 99998. So we're talking about a difference between the error function and 1, which is of the order of magnitude of 10 to the minus 5. And you see what happens here. As you increase through the truncation order, you start by oscillating with the error that you can achieve. And eventually this error can decrease, but it's going to take many, many more iterations. Okay, so I'm just keeping going here. So, but instead of running iterations from truncation orders from 1 to 15, I'm using now truncation orders from 20 to 30. And from 20 to 30, you see that, as I was saying before, eventually, the error starts being smaller than 10 to the minus 5. All right, and so we need in this case 28 terms, and this is only t is equal to 3. We can replicate the same story with t is equal to 4, or maybe t is equal to 5, because the function needs to be evaluated somehow even on this plateau or near the plateau, right? And so if you do that, then you just realize that as you truncate, this is still what we have for t is equal to 3. This is the error that you can achieve. That's the error that you can achieve. And you see that we have, this is not in percent, right? So this is a factor of 100 on the estimation that you could have on the value of the integral, right? This is what we have over here, minus 109 and plus 102. And so momentarily, during the iterations, there's a phase where you add and subtract things that are compensating a lot. And this is because in the different terms we have in the sequence, which are over here at the top and a little bit below as well, what happens is that somewhere in the middle, there's a kind of compensation with the power of x that you have at the numerator and the factorial that comes at the denominator. And it takes a little bit more through the iterations to make sure that the factorial coming in the denominator becomes dominant. And that's even worse when t is equal to 4, and that's even worse when t is equal to 5. All right, meaning that the number of terms that you need to keep for this convergent series to be really efficient after being truncated is actually growing very large. All right, and moreover, you see that the error that you make momentarily grows to larger and larger values. So we started with a value of 100 for t is equal to 3, which is still fine, but the error grows to much, much larger value. You see, 310 to the power 8, meaning that two different terms in that sequence are taking values as large as plus or minus 3, 4, 5, or 6, 10 to the power 8. At the end of the day, they should compensate almost fully because the result of the integral should be equal to 1. All right? So this creates, of course, definitely some round-off errors and makes this approach not really suitable for numerical estimations of the error function. All right, so instead, something else could be done. And what could be done is to transform the integral we're looking for. So the definition of the error function, let me just copy it over here. The error function is the integral from x to infinity exponential of minus t, or maybe let me just drop the error function here and come back just with that integral. That would be easier. Integral from x to infinity of the exponential of minus t squared dt. If we do integrate this by parts, then we have twice t exponential minus t squared divided by twice t dt, which gives exponential of minus z squared, x squared over 2x minus integral from x to infinity exponential of minus t squared over 2t squared dt. This can also be expanded with integration by parts. And this integration by parts can be repeated indefinitely. And if we substitute this into the definition of the error function, that's the error function of z, which would obtain as 1 minus exponential of minus z squared over, x. Let me just use x because I was using x over here. Error function of x, exponential of minus x squared over x square root of pi multiplied by 1 minus 1 over 2x squared plus 1 times 3. This is the double factorial over there. Twice x squared squared plus 1, 3, 5 over 2x squared to the third. Sorry, that was with a minus there, etc., etc. Okay, so you recognize here another series where now the factorial comes in the numerator, and we have the different powers of x coming in the denominator. And so at some point, there will be some terms over there which come a little bit further in the sequence, which are in fact, and unfortunately, much, much larger than the previous terms. And this makes it such that the radius of convergence of this series is the empty set. So there's no single value of x which is such that this series is convergent. All right? No value of x such that this series converges. All right. Okay. However, if we decide to truncate this series, after the first 3 terms, for instance, that's just an example. If we keep 3 terms, we have an accuracy of 10 to the minus 5 when x is equal to 2.5. And the reason for that is that, in fact, even the leading order term, which is here, the leading order term provides already a very, very good approximation of the result. You see, 1 minus something that is going to be very small because of the exponential of minus x squared. All right, and this coming here is a very good approximation. And even if this, at the end of the day, diverges, it is multiplied by something that is quite small, And this is why the truncated version of the sequence, as soon as you truncate it somewhere, provides a very good results. If you want to determine now the accuracy of 10 to the minus 5, again, how many terms do you need? How many terms are required when x is equal to 3? It is easy, right? We can simulate the process in the same way as what we did earlier. The answer is 2 terms. And that's totally crazy, right? Because it means that this is a sequence. It is not convergent, but you don't need so many terms in that sequence to make it work well as x is getting large. All right, so as x grows, I don't want to say x goes to infinity, right? Because we're not talking about super large values of x. We're talking about just x is equal to 2.5 or 2.3. You need less terms in the sequence to provide an accurate estimation. All right. And the problem is that if you would keep all terms in the sequence, that would be bad. All right. And that's clearly the definition of an asymptotic series. All right. So this series is asymptotic. All right, and so just to give you another definition of a series, an asymptotic series, just to make sure we are clear about this, we said that a sequence, which is a collection of functions like this, is, let me use a small number as we write it usually here, is asymptotic if for any value of n that you choose, fn over fn minus 1 tends to 0 as epsilon grows to 0, comes down to 0. Meaning that if you have a sequence of values, like of functions, f0, f1, f2, f3, etc., you just want to make sure if the sequence is asymptotic, you just want to make sure that any term is in fact smaller than the previous term in the sequence, all right? This is called the asymptoticness. Asymptoticness of the sequence. All right, and the sequence might not be asymptotic if epsilon is too large. You just want the sequence to be asymptotic as epsilon goes down to 0. And so this an example of such a sequence, of course, is something we know. We tried these already. If you use a sequence of functions like those, you see that any single term in that sequence is much smaller than the previous one as epsilon goes down to 0. All right, and this is called an asymptotic approximation. All right, I hope this was clear. We're going to use, of course, those asymptotic approximation a lot in perturbation techniques because everything is based on that. There are other examples showing that convergent series and asymptotic series are two things that are completely different. I don't want to mean that convergent series is bad, all right? So I have many friends teaching calculus, and this is very important to understand the radius of convergence of series and that kind of stuff. This is really helpful to understand integrals. I'm just talking about here about something fully different, which is asymptotic series, and which can be only used if you truncate them, all right? I don't want to use asymptotic sequences or series, keeping a very large number of terms in the sequence, okay? And this is also explaining why in many of the problems we deal with in perturbation methods, we keep only the first 2, maybe 3 terms in the sequence, and that's it. All right, I hope you enjoyed, and keep going. Enjoy.